More accurate title here is Physics Predictions for L2 Kernels of Dirac Operators on Monopole Moduli Spaces. And this is work I've been doing for the last few years with Dieter van den Blinken, who's now in Turkey, and Andy Royston, who's at Texas AMU. And there's been a lot of activity in the past 8 years or so on the so-called subject of wall crossing of BPS states. I'm not going to define those terms. And the object of today's lecture is to see what those results from the past 8 years imply for differential geometry, or if you like, for metric and analytic aspects of moduli spaces. And it's actually nice to be talking about both Dirac operators and monopole moduli spaces here in Cambridge, where it all started. So let's begin with monopoles. Review monopoles and singular monopoles and their moduli spaces. So let's let G be a compact, simple Lie group. And we're going to talk about Yang-Mills-Higgs theory on R4. So let's put the action here. So S is equal to the integral over R4 of minus 1 over G naught squared F star F plus dx. X is the adjoint valued Higgs field, dx. And in our paper, we include a theta angle and all its complications, but for simplicity, I'm going to drop the theta angle here. This is a killing form, and the long root squared has length 2. And so we're interested in monopoles. So these are static solutions that saturate a Bogomolny bound. So F is star 3dx when restricted to 3 dimensions. Now, we crucially need boundary conditions on R3. So we choose an element of the Lie algebra. That's my notation for the Lie algebra of G, which is regular. And what regular gets us is maximal symmetry breaking down to the Cartan torus. So that implies a choice of Cartan subalgebra. I'll denote that T, as well as simple roots, alpha I, and co-roots, H sub I, and I here runs from 1 to R, which is the rank of G. Okay? And when we have that data, then, as is very well known, in a suitable gauge, we can write x infinity minus gamma m over 2r plus lower order, and f is 1/2 gamma m times the 4 pi volume form on the 2 sphere plus lower order, where gamma m is the magnetic charge, and so that's an element of the co-root lattice, which is the integral span of the simple co-roots. All right, so when we have that, we have a moduli space of these monopoles. And what do we know about it? Well, we know an awful lot, but just let me summarize 1 or 2 things. We know the dimension, the real dimension is 4 times the height of this. What is the height? Well, if I expand this in simple co-roots, then the height is the sum. This is 4 times the sum of the NMI, and the moduli space is not empty. if and only if the integers here are all non-negative and one is, at least one is positive. Okay, so that's one thing we know. Another thing we know is that it's hyperkähler. And the third thing, which will be very important in what follows, is that there's a Lie algebra of killing vectors. There's isometries. So we can translate our monopole. That won't be so important. We can rotate. These are rotations. That will be very important. And we can make global gauge transformations. So this is translations, rotations, and global gauge transformations. And these are triholomorphic isometries, and the SO3 is not. It rotates the three complex structures into each other. So what is going to be quite important to us is this map from the Cartan subalgebra into the triholomorphic isometries. This is the Lie algebra of M. Maybe I should define that. So the way you define that map is you make a four-dimensional gauge field by taking the three spatial components and thinking of X as the fourth component. And then if you want to evaluate G of H, how do you do that? Well, you solve the equation d hat squared epsilon equals 0 on R3, with epsilon goes to H at infinity, and then G of H acting on A hat is minus the gauge transformation. Okay, so that gives me a Lie algebra homomorphism from the Cartan subalgebra into this triholomorphic isometries. So that's some facts about moduli spaces. Now I want to allow.
Sorry, can you just ask? I guess I didn't understand. You're taking moduli space, but then you still say you have global gauge transformations?
That is correct, because you see, the way we define this moduli space is we quotient the space of solutions by the gauge transformations, which are 1 at infinity.
Okay, so global means that they are just.
So, well, this is what I mean by a global gauge transformation.
Okay.
So this is a gauge transformation which is not 1 at infinity. So, and so it really changes the solution. So these are non-trivial.
Epsilon is in the Lie algebra? Or the
Epsilon is in the Lie algebra. So, right. So epsilon is a map from R3 into the Lie algebra. Yeah. Which goes into the Cartan subalgebra out at infinity. Okay. So it's allowed to be in the Lie algebra, but it has to be going to the Cartan at infinity. All right. So now we're going to allow singularities. So we had a nice talk about that last week. So now let's do singular monopoles. Okay, and we could do many, but we'll just have one of them at x equals 0. And so what's the singularity data? The data of the singularity is a co-character, so something in the co-character lattice. What's the co-character lattice? That's the lattice of homomorphisms from U into the Cartan torus. And it's the dual to the character lattice, which is the other way around, the homomorphisms from the Cartan torus into U1. And in fact, yes, this is a good place to mention that there are a couple of lattices all in play here. So there's the co-root lattice that I mentioned here, which is sitting inside the co-character lattice, which is sitting inside the magnetic weight lattice. And then dual to that is the root lattice, which is sitting inside the character lattice, which is sitting inside the weight lattice. And so this is sitting inside the Cartan subalgebra. This is sitting inside the dual of the Cartan subalgebra. And these are dual lattices, and these are dual lattices, and these are dual lattices. Okay. So now that's the singularity data, and we specify then boundary conditions at r goes to 0, similar to the boundary conditions that we had at r goes to infinity. And what are those boundary conditions? Well, so we now ask that x is minus 1 over 2r times p, r to the minus a half, again in a suitable gauge. F is equal to 1/2 p times the volume form on the little tooth sphere around the origin, dot, dot, dot. This is as r goes to 0. And again, it's in a suitable gauge, and only the Weyl orbit of p is physical. Now, for singular monopoles, we have the same boundary conditions at r goes to infinity, but I put same in quotes because now the magnetic charge is in the co-root lattice plus p, so it's in the torsor for the co-root lattice. All right, so now we have the analogous set of properties for our moduli space of singular monopoles. So we have m bar. It's got singularity data at 0, magnetic charge at infinity, and again, we have a Higgs field at infinity. And what do we know? So the dimension is now equal to 4 times gamma m twiddle, where what's gamma m twiddle? Well, gamma m twiddle is gamma m where we subtract off the image of p in the anti-fundamental Weyl chamber. In other words, this is the Weyl image of p in the chamber where the inner product with all the simple roots is non-positive. Okay, so now this can be expanded in terms of integers times simple co-roots. And we have a conjecture, we have 2 papers about this, where we compute this dimension using the Callias index theorem, and then we conjecture that the moduli space is non-empty, so m bar is non-empty, only if these integers are all non-negative. It's hyperkähler, but it has a singular subloci due to monopole bubbling. That was pointed out by Kapustin and Witten. And again, it has these important killing symmetries. Those are going to be important for us. SO3 plus T. So we have rotations around x equals 0. We have global gauge transformations. But of course, putting this singularity at x equals 0 has broken the translation symmetries. All right, so that's monopole moduli spaces. Now I want to add n equals 2 supersymmetry. So now we add n equals 2 supersymmetry. And I'm not going to explain what n equals 2 supersymmetry is, but I am going to say some of the things it does for us. So one thing it does for us is, so maybe the first and the most important thing it does for us is we have a second Higgs field. So X was a map into the adjoint bundle. So now we have the second one, Y. And in this action here, we now add, now this is supersymmetric, so I'm only writing the bosonic part of the action, and we add dy star dy, and we also add the commutator of xy squared, and again there's theta angles, and if we have singular monopoles around, as we will, then one must also add boundary terms to regularize divergences. And for simplicity, I'm going to leave that out because that's a big, complicated technical story. It regularizes the divergences and gives us finite energies and so on. Now, because of this potential energy term, okay, the boundary condition at infinity is that y is going to go to y infinity, which is again in the Cartan subalgebra. So now we have two elements of the Cartan subalgebra. This x infinity is sitting in here, and now y infinity is also sitting in here. And then the third thing that n equals 2 supersymmetry does for us is it gives us a notion of what are called BPS states. So these are states in the quantum theory. I think they were first pointed out by Olive and Witten, 1978, and their importance was again made clear by Sen and by Zyberg and Witten in 1994. And since then, they've been the object of much study by many physicists. So this is, I'm talking to the mathematicians here who have never heard of n equals 2 supersymmetry, possibly. So the thing, maybe the way you should think about these is that these are quantum analogs of dyons, which saturate a Bogomolny bound. So you, if you've studied monopole moduli spaces, you surely know what that is. And so they're quantum mechanical analogs of those. And the key point here is that our Higgs fields are breaking the gauge symmetry down to the abelian Cartan torus. So there's an abelian low energy gauge group. And so these states have electromagnetic charge. And I'll denote that charge by gamma, little gamma. It lives in a lattice capital gamma, which is the magnetic weight lattice, direct sum the weight lattice. Okay, so you see that's sitting inside the Cartan subalgebra plus its dual. And so notice there's a symplectic structure here. So the symplectic structure is gamma m plus gamma e, inner product gamma m prime plus gamma e prime is equal to, I think it's gamma e dot gamma m prime minus gamma e prime dot gamma m. And that's almost an integer. It's 1 over an integer times this order of the center of the universal cover times an integer. And if I choose suitable sublattices, then I can make it an integral valued form, as will be done implicitly later on. Okay, so I'm listing things that n equals 2 supersymmetry does for you. So we have these states. And it also gives you a nice physical interpretation of what is the meaning of these singular monopoles from a physical point of view. So the singular monopoles, this is number 4, I suppose. The singular monopoles give you what are called 't Hooft line defects. So the picture is that we're looking at monopoles on R3. When we talk about singular monopoles, we put some singularity at x equals 0. And then, of course, we're really talking about physics in R4, R3 times time. And so there's some line defect, which is stretching in time. And it's an electromagnetic dual to the Wilson line, the holonomy of the gauge field. Now, you can preserve 4 out of the 8 supersymmetries doing this. And what's important for us is that these BPS particles can bind to this, line defect. And they also have BPS states. They're quantum states saturating a Bogomolny bound, and they give what are called framed BPS states. Okay. Okay, so now here's the point of this talk. I'm trying to avoid as much physics as I can. But now, when x infinity and y infinity and g naught are in a suitable range, we can discuss these BPS states. We can even define them, as I will in this talk. We can define them semi-classically in terms of the geometry of monopole moduli space. Okay, so if x infinity and y infinity and g naught are in a suitable range, which roughly means that g naught is very small and that x infinity is much, much bigger than y infinity, then the Hilbert spaces of these BPS states can be described in terms of zero modes of Dirac operators on the monopole moduli spaces. So in this case, with the ordinary BPS states, they will be Dirac operators on this moduli space. I'll call that the vanilla because it's plain. Okay, those are the vanilla BPS states, and these are the framed BPS states. They will be zero modes of Dirac operators on that moduli space. Now, how does that come about? That comes about from what's known in physics as collective coordinate quantization. Now, in many of the talks that I've heard at this workshop, reference has been made to Nick Manton's picture of low energy dynamics of monopoles in terms of geodesics on monopole moduli space. And that's the classical mechanics of a particle moving on monopole moduli space. So what collective coordinate quantization does is take that classical particle to the quantum mechanics of a particle on M or M bar. And so this was done in the case of n equals 2 supersymmetry. This was done in a series of papers by Jerome Gauntlet, starting in 1993, then Gauntlet and Harvey, and then Gauntlet and a number of Korean physicists, including Kim-Yon Lee, Park, and Pil-Jin Yi, and I think the last paper in that series is around 2000. And so what you get is super quantum mechanics, of course, and it turns out to be n equals 4 super quantum mechanics. And what we did with Dieter and Andy Royston, and most of the hard work was done by Dieter and Andy Royston, is generalize this story to non-zero theta angle to include singular monopoles. I mentioned that there are these boundary terms here, so it's quite a chore to check that you can choose the boundary terms, preserving the supersymmetries, that you can put in your collective coordinate quantization, and that the boundary terms don't mess things up. It's a lot of work. And also, the third thing is to worry a lot about the role of one loop approximations, one loop corrections to the collective coordinate dynamics, and whether it's valid to include that or not. And in our story, it is. Okay, so the upshot of all that work, and that's an enormous amount of work. This has been a paper in the works for a few years. So the upshot is the following. So to save writing, I'm going to just call x infinity curly x and y infinity curly y. And what we do in the framed case, so finally I'm getting to a definition. In the framed case, we have this moduli space. We now have this data here, and remember we have this G map I mentioned before from T into the triholomorphic isometries. So we consider the twisted Dirac operator, d slash twisted by y, which is the ordinary Dirac operator on M bar plus a G slash sub y. Okay, so that's acting on spinors on the monopole moduli space. And then the definition, key definition, is that the space of semi-classical framed BPS states of charge gamma m is equal to the L2 kernel of this twisted Dirac operator. Okay. Now, notice that I only said the magnetic charge, and fortunately it's still on the board. I said earlier that a BPS state is characterized by a magnetic and an electric charge, the magnetic charge in the magnetic weight lattice, the electric charge in the weight lattice. So what about the electric charge? Well, you see, again, we have this map from the Cartan subalgebra to the isometries affect the whole Cartan torus. So the Cartan torus commutes with the Dirac operator and acts on this, and so we can write an isotypical decomposition. So the kernel, the L2 kernel of Dirac, then can be written as a direct sum over the weights in the weight lattice of what I'll call the framed BPS states of charge gamma with boundary conditions x and y. Okay, so that finally defines our space of framed BPS states. And there's one more thing to say here. And a few more things to say. It's also true that SO3 acts on these spaces. Now, SO3 doesn't quite commute with the Dirac operator, but nevertheless it preserves the kernel. I'll explain that in more detail if there's a question. But SO3 acts, so these spaces are also representations of this SO3 of rotations. Furthermore, because M bar is hyperkähler, there exists an SU2, what physicists call an SU2R symmetry, which acts on the tangent space. So it's the SU2 which is in the commutant of the SPN holonomy, and it acts on the tangent space and it rotates the three complex structures. And that SU2R lifts to the spinor bundle, and again, it doesn't commute with the Dirac operator, but it does preserve the L2 kernel. So this is in fact a representation of SO3 plus SU2R. Are there any questions? This is a crucial point. Okay, yeah, Meredith, hi.
Hi. So just a very basic question. So this definition holds in this suitable range?
That's right, yeah.
And what happens?
Well, I mean, if the quantum corrections become important, then I won't make any guarantees about it. Yes, there might be. Yeah. I mean, there could be walls, for example, if you try and come in from the semi-classical regime. Yeah.
There's only one semi-classical.
Pardon?
There's only one semi-classical.
Oh well, there's lots of space out there. I mean, it's most of it's X is large, and so you're in the Cartan torus. I mean, there are plenty of predictions for differential geometry. Okay. In fact, while
Sorry,
I'm
this is on the spin bundle tense the adjoint bundle of this Dirac operator? Or
no, the Dirac operator. This is just acting on the spin. This is just on the spin bundle.
Right.
So G was a vector field.
Yeah,
and then I've used the metric to make it a one form, and then this means Clifford multiplication by that one. Yeah, sorry about that.
Yes, no, that's fine.
So, okay, so yeah, actually, maybe let me say one more thing about the answer to Miranda is, let me give a little transcription for physicists. Physicists might have expected me to say, well, there's an H of gamma and the U for the U plane, so where's the U plane? So physicists might also have objected by saying, well, when you gave your singularity data, you gave this co-character P, but a line defect actually requires a P and a phase zeta, where zeta is in U1, telling me which of the 4 out of 8 supersymmetries are preserved. So the relation to that physical data is that curly X is the imaginary part of zeta inverse A of U. This is notation I'm not explaining because this is aimed at physicists who know what this notation means. And then you take the one loop approximation to A dual of U. And so this gives you the map from the U plane, or the Coulomb branch, and this phase zeta to the parameters I'm calling x and y. And so, Miranda, as long as the one loop approximation is a good approximation, that what I'm saying is correct. Okay, so we have these spaces of BPS states, which have now been defined in terms of the L2 kernel of the Dirac operator. Well, I've just done the framed case, so now I want to do the vanilla case, which is very similar. So in the vanilla case, we have this moduli space, and it has the technical complication that it's reducible because of the center of mass degrees of freedom. So if we take the universal cover of that moduli space, we have R3, and then we have one overall global gauge transformation. I'll say what that is in a moment. And then what we have is what's called the centered moduli space. And this R are the orbits of our G vector fields, our triholomorphic vector fields in the direction x infinity in the Lie algebra. So now we take the Dirac operator twisted by y, and we split it in terms of the center of mass part and the relative part. And so now we can give the analog of this definition here. So what is that? So definition, the space of semi-classical BPS states, if you like vanilla BPS states, of magnetic charge gamma m is just the kernel. Well, it's really the kernel of the Dirac operator. So it's the kernel of the Dirac operator on the centered moduli space. And then it also, to be in the kernel of the center of mass, we have a constraint that gamma m y plus gamma e x is 0. That this condition is just for the spinner to be in the kernel of this guy. Okay, now once again, this is acted on by the whole Lie algebra of global gauge transformations. So we again give an isotypical decomposition, just like we did before. And I'll denote these spaces by h of gamma x, y. And the same story I gave before means that this is a representation of SO3 for rotations plus the SU2R symmetry rotating the complex structures. Okay. Are there any questions about that? So that's all been review of old stuff. So now I'm going to add a slightly new point. Okay, so this, I think all of this was known in 2000, although maybe people wouldn't quite have said it this way, but well, maybe not the singular monopoles. And the framed BPS states. Okay. Now, there's a conjecture called the, I'll call it the no exotics conjecture. Okay, no exotics conjecture. It came out of some work with Davide Gaiato, myself, and Andy Knightsky, 2010. And it says very simply that SU2R acts trivially on the H bars and the H's. Okay, so it's a conjecture. It's for general super Yang, general n equals 2 field theories, but it's been proven for super Yang-Mills theory with gauge group SUN by Diaconescu et al. Jan Manscott, a bunch of people. And for G simply laced by Ashok Sen and Michele Del Zotto. Okay, and the techniques that use this are completely foreign to the kinds of things I'm saying. They use quiver varieties. So you look at the motivic type of quiver varieties, and it implies that SU2R acts trivially on the BPS states. Now, what does that imply? So it's true for the cases that I'm discussing. So what does that imply for these spaces that we get from the isotypical decomposition of the L2 kernels of Dirac operators? Well, it implies two things. First, we have a map of SU2 times USP to n into spin for n, where the moduli space is of dimension for n, which takes the -1,1 to the canonically oriented volume form on spin n. And the orientation is given by any of the complex structures. And therefore, since this SU2R is acting trivially, this implies that the kernel, the L2 kernel of Dirac, is chiral. That is to say, gamma bars plus 1. So one of the reasons I'm giving this talk at this workshop is that I'm asking the mathematicians, is this obvious? Is this trivial? Is it interesting? I'm proceeding on the presumption that it's not obvious and perhaps interesting, but I'm not sure. I'm not sure what's known. So the other thing is we can use Hitchin's thesis, telling us that we can identify the spinor bundle with the anti-holomorphic forms, and then the twisted Dirac operator becomes the twisted D-bar operator. So we have D-bar plus the 0,1 part of G. This is G naught of Y wedge, okay? So I'll call that the twisted D-bar operator. And so what does the no exotics conjecture tell us? So no exotics tells us that if we look at the L2 cohomology of this twisted D-bar operator, it's 0 if Q is not equal to n. In other words, it's concentrated in the middle dimension, and it's primitive if Q is equal to n. And again, that kind of resonates with the talk we had last week about L2 cohomology. Okay, so that's the no exotics conjecture. So that's one set of physics predictions about these L2 kernels. So now I want to talk about wall crossing.
Sorry.
Yeah.
So could you clarify the relation with what Sen did? I mean, Sen looked at things this way, but in n equals 4.
Well, he was in n equals 4,
wasn't he? But he
and
is that a theorem for Sen?
no, he was not. He was looking at harmonic forms. I think they were type 1,1. It's different from Sen. It's.
Well, type 1,1 only in 4 dimensions.
Okay. So
Sorry, no.
it was. I think it was. I thought they were one. I thought.
Sorry,
I thought they were 1,1, and I thought they were 1,1 in all.
This last remark looks like the.
It's definitely reminiscent of Sen, but it's. I'm pretty sure it's different. He didn't have this twist. Yeah, let me remark about that actually. You see, if we put y equals 0, then we have the ordinary Dirac operator. So by the Lishnerovitz formula, something in the kernel of Dirac is a covariantly constant, and if we ask that it be L2, it doesn't exist. So this y is completely essential, and I don't think he had that.
Sen had no y, right?
He had no y. Yeah. I mean, I worried about this, and And I concluded that this is really rather different from what he was doing.
I thought sen was L2.
It was L2 harmonic forms, that's for
Yes,
sure.
yeah.
In middle dimension.
But the prediction was that it was non-zero only in the middle dimension.
That's
And if
correct.
there's
That's
some kind of
correct. So this
finality
certainly
between-
resonates with that. Yes.
And I think also, I'm not quite sure this word primitive means, but I think his.
Oh,
form
it
was
means that the
primitive.
Lefschetz SL2 is acting trivially on it.
So there's a notion of primitive to sen, which involved the coprimality
Yes.
of the gamma
That,
mu.
that's
and
true,
the
that's true.
gamma
So there
and
was the
the
P and
gamma
the
E.
Q, and they had to be, yes, that's right.
Right,
That's
so
right.
it sounds a very similar flavour.
It's most definitely a similar flavor, and that's not surprising because he was talking about n equals 4 supersymmetry, and we're talking about n equals 2 supersymmetry.
So there's no formal limit of an n equals 2 theory to give you an n equals 4 theory in the way you're presenting it.
No. No, I don't think we can easily enhance the n equals. Oh, you want, well, let's see. You see, we could do something. You could start with n equals 4 and you give some masses to some of the adjoint fields and break that down to n equals 2, and that's called the n equals 2 star theory. But that's another theory. That's this theory plus a hypermultiplet. Okay, and so again, it's a different theory. So it's a different operator. I think it's a different prediction, although I completely agree that it's a very similar flavor to what Ashok did in 1994. Okay, so yeah, I think he was looking at a different, yeah, I'm sure he was looking at a different supersymmetric quantum mechanics on the moduli space of monopoles and so on. All right, so now I want to talk about wall crossing, and as I said at the very beginning of the talk, there's a great deal of work that's been done on wall crossing over the past 8 or 10 years or so. And the question is, well, what does that imply for these L2 kernels of Dirac operators? So now I want to say something about that. How much time do I have to say it? Not much. Okay, so so what we want to do is we want to look at this family of Dirac operators as we vary y. In principle, we could also vary x, but then we're varying the actual monopole moduli spaces. We'd need to put a connection on that family of spaces, and we didn't do that, but I'm sure it can be done. Anyway, let's just consider varying y. So we have a family of operators, and they're generically Fredholm. Okay, and because the kernel is chiral by no exotics, that means the dimension of the kernel is the index, and so that implies that these SO3 characters of H and H bar are piecewise constant. But they do jump on walls. And so the question is, where are those walls? So let me say it for the vanilla and then the framed case. So the prediction is that the Dirac operator on the centered moduli space is not a Fredholm when there exists two electromagnetic charges, gamma 1 and gamma 2, such that their symplectic inner product is not 0, such that the these spaces of BPS states for these two constituents, as they're called, are not 0, and such that they satisfy this center of mass constraint. Okay, so that's where they fail to be Fredholm. And then what jumps? What jumps? Well, if I define gamma as gamma 1 plus gamma 2, then the space H of gamma xy jumps. How does it jump? Well, in general, it's governed by something scary called the Kontsevich-Soibelman wall crossing formula. But I'll give a simplified version of that in just a moment. So something you can hang on to. This is from 2008. Okay, so let me first say what the jumping is for the framed case. Now it's going to be d slash sub y is Fredholm except at walls which look like this. I'll write W of gamma sub h. For experts, the sub h is for halo, so it's just some charge, such that the unframed, the vanilla space, okay, we're talking about the jumping of these spaces, but the walls, the place where it fails to be Fredholm is governed by the unframed, the vanilla states. So this has to be non-zero, and again, gamma h magnetic, y plus gamma h electric x is equal to 0. Okay. And so then the claim is that h bar of gamma, p gamma x and y, jumps if gamma h gamma is not 0. Now I can tell you how that jumps. Okay, so here's the formula for the jumping. It's kind of amusing. So to write the formula for the jumping, you introduce the Heisenberg extension of the group algebra of gamma. Okay, so for every electromagnetic charge, little gamma, we introduce a formal variable x sub gamma, not to be confused with the Higgs field. I just realized that's terrible notation, but too late right now. So this is a formal variable, not a Higgs field. So x gamma 1, x gamma 2 is q to the gamma 1, gamma 2, x sub gamma 1 plus gamma 2. Okay, and then we form an element of this Heisenberg algebra associated with our singular monopole data P, where we sum over the charge lattice of these things called the framed indices, x sub gamma. And what are these? These are the SO3 characters. So they are the traces of q to the 2j3. J3 is a generator on h bar. So they're Laurent polynomials in Q. Okay? So that's the second element of the jumping formula. Now for the third element, I also need the character of the unframed BPS states, the so-called halo states. So let's write omega of gamma halo. Remember, we're jumping. I'm telling you the jumping as we cross this wall. Okay, the wall defined by this equation. So this also has a Laurent expansion. Let's call it a sub m minus q to the m. So these m's, a sub m's are integers. And so finally, if y crosses this wall, w gamma h, then the formula is that this generating function f of p gets conjugated by s sub gamma h, f of p. Remember, we're in a non-commutative algebra. And what is s sub gamma h? S sub gamma h is the product over m of phi of minus y to the m, x sub gamma h to the am, where the phi of x is what's called the quantum dilogarithm. So this is the product from k equals 1 to infinity of 1 plus y to the 2k minus 1. So this looks incredibly scary, but it's actually extremely simple. It's just a mathematical way of saying that one is creating some Fock spaces of binding particles as you cross the wall. Now I can say what the Consaver-Soibelman formula is. It's simply that a bunch of products of these things is constant as a function of y. and I did indeed. I changed notation. I usually call it y. And I changed to q because I'm using y for this second Higgs field. So the Kontsevich-Soibelman formula, I'm going to skip the Kontsevich-Soibelman formula because I have 5 minutes. There's a very simplified version of it called the primitive wall crossing formula, but I was only needing that for a nice example of vanilla wall crossing, which I don't have time for. If someone's interested, I can give you a clean example of what this wall crossing looks like on Taub-Nut space for SU3 monopoles. But let's skip, that's essentially contained in an old paper of Jerome Gauntlet and Kim, Park, and Piljin Yi. So let's talk about a new prediction. So this is example 2. I'm skipping example 1 because of time. So let's give an example of framed wall crossing. So now we'll just take SU2. So our Lie algebra is SU2. So our singularity data is just an integer p over 2 times h alpha, the simple co-root, if you like. H alpha is just minus I times 1, 0, 0, minus 1. Okay, p is an integer. And so now we form this generating function, which I don't think I need to write again. It's right up here. And let's parameterize our charges of our framed BPS particles as magnetic plus electric. So gamma magnetic is some integer n tilde sub m minus 1/2 p times h alpha, and gamma electric is n e times alpha. Okay, and I've defined it in this funny way so that by our dimension formula, the dimension of m bar is 4 times nm tilde. Okay. In particular, I'm going to tell you some prediction for the kernels of Dirac operators on monopole moduli spaces of large dimension. Okay, so now I told you that the framed states jump across these walls determined by where the vanilla or unframed particles are existing. And that BPS spectrum for pure SU2 theory is extremely well known. So W of gamma halo is just the space of Y's. And the halo is now parameterized by an integer n. So H alpha Y plus N alpha X is 0. Okay, so pretty much just copying that. And so here's our Cartan subalgebra. Y lives here. There are walls, W of gamma n, W of gamma n plus 1. And in between those walls are chambers, Cn. So now finally I'll write a formula for this generating function in chamber Cn. Okay, so now this formula is coming out of the blue, okay? It comes from the whole theory of line defects and so on. So it's going to look like magic. So the formula, you can either get it by summing up wall crossings. So I gave you some concrete formula for how these omega bars jump, or from what's called the 6-dimensional 2-0 theory. So there's a certain quantum field theory in 6 dimensions, which leads to the following prediction. So if we put Q equals 1 for simplicity, so if Q is 1, if my Heisenberg is still here, okay, then these things now become commutative. Okay, so let's write x1 is x sub h alpha, and x2 is x alpha. So now commutative variables. And then the claim is that this generating function has the following form. It's x1 to the minus 1/2, x2 to the minus n plus 1 over 2 times, and I'll define this notation, So the t's and the u's are Chebyshev polynomials. And the whole thing is raised to the absolute value of p power. And so the Tn is x1 plus x2, x1 to the n plus 1 plus 1 over t square root of x1. I'm just writing all this out to show you there's very, very explicit predictions for the dimensions of these kernels and in principle also for their characters, where Tn is the Chebyshev polynomial. So that's cosine of theta, and un is the other one. Okay, so these are some polynomials. So you expand this out, you get some big Laurent polynomial in x1 and x2. X1 is going to be raised to a power which is going to be the dimension of the moduli space minus p over 2. X2 is going to be to some other dimension determining the electric charge, and the coefficient of that is the dimension of the kernel of the L2 Dirac operator on this monopole moduli space of SU2 monopoles with dimension, framed singular monopoles with the dimension 4 and tilde. So that's a very explicit prediction. So let's.
Thank you very much. Any questions?
In a physics sense, are these jump conditions expressible with stress energy tensors? Is that meaningful here?
Well, yes, in the following sense. This is probably not what you had in mind, but they're certainly expressible in terms of energies.
Because I mean, maybe the leading point would be, in some sense, the motion of these objects if one was.
Okay, so they're only BPS when they're at rest.
Yeah, that's right.
Okay.
So that's
So the BPS bound says that the energy of the state is equal to what's called the absolute value of the central charge. Okay. So we have this electromagnetic charge, gamma m plus gamma e. And there's a complex number associated with that, which is the inner product of this gamma m with a plus gamma e times a dual. And so there are some vectors, some complex vectors that give me a formula like this. So it's linear in the central charge. Now, if I have some particle and I want it to decay into two particles of charges gamma 1 and gamma 2. Okay, so electromagnetic charges have to add. So z gamma is equal to gamma 1 plus gamma 2. So the z of gamma is equal to z of gamma 1 plus z of gamma 2. But you see, there'll be a non-zero binding energy unless this is equal to the absolute value of z of gamma 1 plus the absolute value of z gamma 2. That's why I'm answering your question about stress energy tensors, because I'm talking about binding energies. Okay? Now, when does this happen? This happens only when these two complex numbers, gamma 1 and z of gamma 1 and z of gamma 2 are parallel. So you definitely have a very simple energetic condition on when you could possibly have these BPS states decaying.
Anything else? I'd just like to say that one of my hopes for this program was that mathematicians would get some appropriate challenges for the next 10 years, and I think this talk has certainly given us a lot to think about. So let's thank Greg.